In this video, we'll discuss the length of a curve C given by a vector valued function r of t. We'll also discuss the arc length parameter starting at a certain point, which we'll call the base point P. We'll discuss why we might choose to use the arc length parameter to parameterize our curve rather than the time parameter t, and then we'll use our arc length parameter function to come up with this, and then talk about why this really makes a lot of sense. So let's just review. If I have a curve C given by r of t in three-dimensional space, r is going to have components x of t, y of t, and z of t. And remember what that means. For all t in the domain, we're going to have some curve. Maybe as t increases, we're going this way along this curve. It's a one-dimensional object that lives in three-dimensional space. As t increases, we just trace that out. And the vector r of t is a vector that starts at the origin and points to a certain location, and it says this is where you are here. So we can think of this as a position vector, and we can think of this as the position x of t, y of t, z of t of some object at a certain time. Now, it does not have to represent that. T could represent something else, but it's helpful for me to think of this as taking a time t and mapping it to a certain location. So we tend to think of these this way, and our location can be in 2D, so it would look like this, or 3D, so it'll look like that, or it can be in n dimensions. And we wouldn't be able to visualize it, but the principles would be exactly the same. Now in this section, we're talking about the length of the curve C. Now, when I say length, I mean a literal length. If this is 1 unit in the x direction, this is 1 unit in the x direction, this is 1 unit in the x direction, the length from here to here is 3 units. I don't know what what 1 unit represents in terms of inches or centimeters or feet or meters. We're not too concerned about that, but this is just 1 unit of distance in this coordinate system. And if I'm consistent, well, that's 1 unit of distance, and that's 1 unit of distance, and that's 1 unit of distance. So when someone talks about finding the length of these curves, sometimes they'll call it arc length. It's probably what you called it in Calculus 2, was arc length. They're talking about how long this is. Like literally, if I had a string and I laid it along the curve, and I just set it there, and then I took the string and I stretched it out, and I went from here to here, and I said this is the starting point, and now that I've stretched it out, this is the ending point. How long is it? Well, we would just count, or we would measure, and we would find out how long it is. Problem is we can't do that. We don't have a string that's lying along this red curve in three-dimensional space. So we need some other way to come up with the length of the curve. Now back in Calculus 2, we did this in 2D. We said if we have a curve given by y equals f of x, we could do something. And we also talked about parametric curves in Calculus 2. We said maybe this is a curve given by parametric equations x of t, y of t. At that point, we hadn't learned about vector valued functions yet, but we were learning about the parametric equations that generate this vector valued function. Do you remember what we did in Calc 2? Now, this was not from Calc 2, but this is just r of t in the plane. We did what we always do when it comes to integration. If we're trying to find the length of something and it's curving, we say, oh gosh, that's a problem. I don't have a formula from pre-calculus that will allow me to find the length of this curve. And then we said, but that's okay. If I break this up into n little pieces, and then I look at the length of one of these pieces, it's approximately linear. And if it's approximately linear, I can approximate that by the distance between that point and that point. And so we said, if this is x sub I, y sub I, and this point is x sub I plus 1, y sub I plus 1, then this little distance, which we're going to represent by delta s, well, that can be found using the Pythagorean theorem. There's a tiny triangle there. Let's zoom in a little bit. So like focus on this, but zoom way in. If I zoom in, what am I going to see? I'm going to see a triangle like this. And my curve looks kind of like this. That curve, the length of that curve, we're representing by delta s. And this is a change in the x values. It's x sub I plus 1 over x sub I, so delta x. And this is a change in the y values, so delta y. And this squared plus this squared has to be that squared, approximately. And then we did something that was a little proofy. It wasn't exactly proof, but it was proofy. We said, okay, I'd really like to be able to integrate this. I need some variable to tie together this x, this y, and this s. I said, well, if I'm on a parametric curve, I have the variable t to tie them all together. Do you remember what we did? We divided everything here by delta t squared under the radical. And we said that's legal as long as we also multiply by delta t squared, so we're not changing anything. And then we said, hey, let's simplify that a bit. Isn't that the same as this? Square root of delta t squared is delta t, provided delta t is positive. We're going to assume it is. And then we said, let's add all of those up and take the limit as the number of pieces goes to infinity. And eventually we ended up with this integral. We said the length of the curve is the integral from a to b of the square root of x prime squared plus y prime squared. And we're integrating with respect to t. Now we said back then that at t equals a, we're at that location, x of a, y of a. And at t equals b, we're at this location, which is given by x of b, y of b. So we've done this before. We didn't have parametric we had parametric equations, but we didn't have r of t yet. That's okay. We were able to come up with this by splitting this into a bunch of little pieces, finding the length of one piece, or approximating the length of one piece using the Pythagorean theorem. We could do exactly the same thing here, but I want to point out something else about this formula. This looks like something. It looks like something that we've already studied in Calculus 3. Do you recognize it? I hope you do. It's okay if you don't. But I've got a square root, and I'm taking things, I'm squaring them, and I'm adding them together. What do we square and add and then take this, when do we square components and add them and take the square root? What's that called? Do you remember? I hope you said that it's magnitude. It is the magnitude. If r is given by x of t, y of t, so we're in 2D, then r prime is given by x prime of t, y prime of t, right? Because it's how we take the derivative component by component. Now, if t represents time, this is our position vector, and this is our velocity. So what this says, if t represents time, is that the length of the curve is the integral from a to b of the magnitude of this. It's the magnitude of r prime of t, or the magnitude of the velocity times time. And I think that makes a lot of sense. Let's think about the physics. What does this represent? Isn't that speed? And isn't this an infinitely small time, infinitesimal time? So I'm taking speed, which is change in distance per unit time, and I'm multiplying it by a tiny time, and then I'm adding all those together, and I'm saying, well, that's the total distance traveled. Now notice this is not r prime times dt. This is the magnitude of r prime times dt. So I've got distance, so I've got change in distance per unit time times a tiny time. And then I add that up, and that's total distance traveled. So this makes a lot of sense. This is what we did in 2D back in Calc 2. This formula stays exactly the same in Calc 3. We just didn't call it this in Calc 2. We called it this. But it's the same thing. So this holds in 2D, and of course in 3D, r looks like this. So I can take its derivative, and it looks like this. I'm just going to drop the dependence on t, but you know it's there. And then when I take the magnitude of that, I get the speed. So this is our equation for the length of a curve, starting at the point associated with t equals a. So this is x of a, y of a in 3 dimensions. If we're at this location when t equals a, that's going to be x of a, y of a, z of a. So at a particular time, we start there. And then sometime later, we're over here at this point. And maybe that point is given by t equals b. So at that point, at that time, we're at x of b, y of b, z of b. So these are telling me times, and those are telling me locations. I'm going to say, well, how long is that path? If this is a position that I've been traveling along from this time to this time, how far did I go? How far did I travel if I'm traveling along this path? I don't want my displacement. I don't want this position minus this position, because that's not the same as how far I traveled. The distance that I traveled is the length of that curve. And that's exactly what we're finding here. So that is our equation for length. Let me give you an example. Let's say you're asked to find the length of this curve. Curve C, where C is given by r of t, and r of t has these components. It's 12 times sine of 2t and 12 times cosine of 2t times j hat plus 5t times k hat. And we want to find the length of the curve from t equals 0 to, let's say, t equals pi. Alright, let's do it. According to our formula, the length of the curve is given by the integral from a to b of this. Now if I'm thinking of this as a position function, they're asking us the distance traveled from time t equals 0 to time t equals pi. How long did I travel if I'm going at this speed for this amount of time? So in order to use this formula, I need to compute r prime, I need to find its length, I need to integrate it from t equals a to t equals b. So let's go through each of those steps individually. First, we'll compute r prime. So you just take the derivative of r component by component. Ooh, I don't think I like those 2's coming out. Let's change this a little bit. Let's make those 6's. Okay. So now that those are 6's, when I take the derivative of that, the derivative of 6 times sine of 2t is 6, and times the derivative of sine of 2t. And the derivative of sine of 2t is cosine of 2t. Got that inside function now. Times the derivative of the inside by the chain rule, so that's a 2. And then I'm going to bring this 6 down. Got another inside function again, so we've got to use the chain rule again. Derivative of cosine is negative sine of the inside function. And then we multiply by the derivative of the inside by the chain rule, negative 2. And then the derivative of this constant times t is just the constant. So I've got 12 cosine of 2t minus 12 sine of 2t and 5 as my components. If I want to use this formula, the next thing I need to do is find the magnitude of r prime. Now in general, the magnitude of r prime is going to be complicated. How do we find the magnitude of a vector? Remember, we take the components, we square them, we add them, and take the square root. That's usually not going to simplify. I mean, if this was just a 2t as a component, you take 2t and square it, you get a 4t squared under a square root. Unless you're not adding anything else to that, it doesn't simplify nicely. But with the trig functions, this one actually does simplify nicely. So let's find the magnitude. Take the components, square them, add them, and take the square root. That's how we find magnitude. Okay. You've got a product here. Square each part. 12 squared is 144. And then we're multiplying by cosine squared of 2t. And negative 12 times negative 12 is positive 144 again. And we're squaring the sine function. And 5 times 5 is 25. Now notice that these two terms have a 144 in common, so we can factor that 144 out. You see it? You see it coming? I know my Diffie students love to see this identity coming. So that means everything's going to get simpler real quick. When I take out the 144, I have 144 times cosine as my first term, and 144 times that sine squared is my second term. So I've got cosine squared plus sine squared. The angles are the same. That's nice. That's 1. Isn't that nice? So we end up with 144 plus 25. That's 169. And square root of 169 is 13. So that's really nice. That is convenient. We just found the length of r prime of t, and that's 13. Now again, if you want, you can interpret all of this. If this is some path traveled by some object, some little object is walking along this path, this is the velocity of that object. And then when I find its magnitude, I found its speed. So if this is speed, this is 13 units of length squared per units of time squared. So this is 13 units of distance per time. Or if we're in meters and seconds, this is 13 meters per second. So this particle is traveling along this path at a constant speed. That's nice. Now most of the time, the speed's not constant, and these guys aren't going to cancel. But a lot of the textbook problems that we have, we've got the sine and the cosine, they're a little bit contrived so that we can get nice answers like this. Alright, so we found the magnitude of r prime. First we found r prime, then we found its magnitude. Now we've got to integrate it from t equals a to t equals b. Now t equals a and t equals b were given. From here we see a equals 0, and here we see b equals pi. So we're just going to integrate our speed function with respect to time. So I could think of this as meters per second. Let's just think of it that way because I think it's helpful to understand what this really means. We're integrating from t equals 0 to t equals pi. R prime, the magnitude of r prime is 13, and I'm multiplying by a tiny dt. So this is like 13 meters per second times a tiny number of seconds. Does an infinitely small number of seconds. So when I multiply these together, I get a tiny change in distance, a tiny change in distance traveled. We're going to keep doing that for all the distances between t equals 0 and t equals pi. And that's going to give us a total distance traveled, or a length of the curve. And so if I'm going along this path from t equals 0 to t equals pi, the distance that I traveled along that path is given by this integral. And it's a simple integral. The antiderivative of a constant is the constant times t. Plug in t equals 0 and t equals pi and subtract, and you get 13 pi minus 0, or just 13 pi. And that is your distance. If this is in meters per second, this is going to be in meters. So that's the length of the curve. The length, if we're thinking geometrically, or if we're thinking of r as representing position as a function of time, it's the distance traveled along the curve by an object that's traveling along that path. So let's actually look at this path and see what we're talking about. R of t has these components: 6 sine of 2t, 6 cosine of 2t, and 5t. Let's see where we are at t equals 0. At time t equals 0, we have 6 sine of 0, 6 cosine of 0, and 5 times 0. Sine of 0 is 0, cosine of 0 is 1. Of course, that's 0. So we're at the location. X equals 0, y equals 6, z equals 0. And that's the negative y-axis. The negative x-axis is going behind us. There's the z-axis going up. Okay, so that is our position at time t equals 0. That's a vector. It goes from there to there, but the position, it's x of 0, y of 0, z of 0, is 0, 6, 0. So that's our location. We're right there. You'd say, okay, Ms. Townsend, what does that mean for us? What does that tell us? Well, we've got to think more about what happens here. Now, if I'm in the plane, remember, if I've got sine of 2t here on my x component and cosine of 2t over here, and the constants and the numbers multiplying those out front, those are just constants rather than functions of t, we're going to be on a circle. It's a lot like in trig when you were on the unit circle. You were looking at this. We had cosine of theta for x and sine of theta for y, and that was theta. And as theta increased, we would go around this way. We can think of that as a vector in the plane. We can think of that not as a single point, but as a vector. And as theta changes, we're going around in the counterclockwise direction. So this is very similar, but instead of being on a unit circle, x squared plus y squared is now going to be 36. It's going to be 6 squared. If you don't believe me, you should check that out. But we're going to go up, we're going to be going around and around on a circle like this. So this is what it looks like from above. Here's the y-axis and here's the x-axis. The y values are all between -6 and 6 because cosine's always between -1 and 1, right? So the y's are between -6 and 6. And the x's are always between -6 and 6 as well, because sine is between -1 and 1. If I multiply it by 6, then this is going to be between -6 and 6. So my x values range from -6 to 6. And you should check it out. X squared plus y squared is going to simplify to 36. After you factor out the 36 and you see the sine squared plus cosine squared is 1 and all that jazz, you're going to end up here. Now this is what it looks like from above, but as t increases, instead of going in the counterclockwise direction, because the sine and cosine were flipped, we're going to go in the clockwise direction. If you say, Ms. Townsend, how do you know? Plug in some t values and you'll see at time t equals 0, x is 0, and y is 1. So we're actually starting right here at time t equals 0. And at time t equals pi over 2, sine of pi and cosine of pi are actually down here. That's t equals pi over 2. Maybe we should try pi over 4. At t equals pi over 4, we've got sine of pi over 2, so that's 6. This is what it looks like from above. So our particle, if our particle is traveling along a path that's given by these equations, is traveling in a circle like this, kind of. What's happening to the z component? It looks like as you go up the circle, so here, z is 0. But as t increases, here, z is this t value, pi over 4 times 5. So we're going to be going up the circle. And at t equals pi over 2, z is 5 times pi over 2, so we're going up. And at t equals, I think this is 3 pi over 4, you should check. Take that, and we're going to go up. And at t equals pi, we're going to be back at this location, but instead of z being 0 this time, now z is 5 pi. And so we're just continuing to go up. It's like a staircase. It's a helix. Because we're going around and around in a circle, but the whole time we're going around and around in a circle, or what would have been a circle, we're going up and up and up. Or over here. We're going to try to draw the same thing. Now, we're doing that from t equals 0 to pi. So we've just seen from t equals 0 to pi, we only do one rotation, so we don't actually go all the way around. But at t equals pi, let's see what we get. Z is 5 pi. This is not to scale. We have sine of 2 pi. Sine of 2 pi is 0. And cosine of 2 pi is 1. So we're going to have 6 times cosine, or 6 times 1, which is 6. So at time t equals 0, we were here. And at time t equals 5 pi, we're at this point in the xy, or in the yz plane right here. So that's 0 for x, 6 for y, 5 pi for z. And we got to that point by going around and around, but on a cylinder. You might say, oh, Miss Townsend, how do you know you're on a cylinder? Okay, let's check. Let's check and make sure that this works. So let's just take our x and y and square it. So here's x, and here's y. Let's square those and add them together, and then see what we get. X squared plus y squared is 6 sine of 2t, quantity squared. And then I'm adding 6 cosine of 2t, quantity squared. Square the 6, square the sine function, square the 6, square the cosine function, factor out the 36, and do you see it? I've got 6 squared, or 36 times sine of some angle squared, plus cosine squared of the same angle. And that's 1. You say, oh gosh, that was a real mess. It is. I'm sorry, it doesn't look very pretty on that piece of paper. But let's go over here. So our curve lies along this cylinder. We've got x squared plus y squared equals 36. Now there's no z in that equation. Z is equal to 5t. Z is free to be anything on this cylinder, but on our path, z is increasing as t is increasing. So we are on a cylinder that's centered at the origin. The radius of that cylinder is 6, so it looks like this in the xy plane. And then we're going around that cylinder to get from this point to this point. And we only go around once to get from t equals 0 to t equals pi. That's just one revolution on that circle. So let's draw the rest of our cylinder. Just do the best you can. These pictures are hard to draw. And then we're going to see the same shape up here. Okay, so that's our cylinder. And as t increases, at t equals pi over 4, we're here, where x is 6, y is 0, and z is 5 pi over 4. So we're going to be over here, but in the xz plane. This is 5 pi, this is a fourth of that. So we're on the edge of that cylinder, like this. And then at negative pi over 2, we're on the y-axis. I said negative pi over 2. That's pi over 2. We're going to be on the y-axis. Y is going to be negative 6. X is still 0, but z is 5 times pi over 2. If this is 5 pi, we're halfway up at that point. So we're going around our cylinder. And then back here, it's going to look like this. And eventually we get to be there. I didn't do a very good job showing that, but something like that. It's supposed to go all the way around. It's a little difficult to see. But we're going on this spiral around the outside of the cylinder, and that's what this represents. Say, okay, what does that have to do with the length? Well, if this is our position as a function of time, this is our speed of 13 meters per second. If I integrate that speed of 30 meters per second with respect to time, meters per second times seconds is going to give me a tiny change in meters. We're going to add those up, and it turns out that we've traveled 13 pi meters as we go from this point all the way around the outside of our cylinder and get back to the same, it's like the same point. It's on that side, but it's higher. It's at 0.65 pi instead of 0.60, which is right down here. Okay, so that's the length of the curve. Now we're going to change this viewpoint just a little bit. Instead of trying to find the length of a curve, we might want length as a function of time, or distance as a function of time along the curve. So distance traveled so far as a function of time. Now, if R represents position, again, this is giving us a distance traveled. We also call this the arc length parameter with base point P. And P is going to have coordinates, if we're in 3 dimensions, x of t naught, y of t naught, z of t naught. Okay. So we're going to start at t equals t naught, and then we're going to go to some other value, some other t value, probably more than t naught. And then we still want to integrate this speed with respect to time. But we're using time as our variable right here. Our variable is actually in the limit of integration. So I need a different variable here. Our textbook author likes to use tau as the dummy variable, but it could be any variable. You could use u. With other textbooks that I've used, they've done r prime of u, its magnitude times du. This is just r prime of tau d tau. And this is giving me the length after a certain amount of time has passed, from t equals t naught to some time later. So if this is my curve, maybe it looks like this. Maybe at time t equals t naught, we're right here. And that's P. We're at location x of t naught, y of t naught, z of t naught. Now when t equals t naught, I'm at the integral from t naught to t naught. And we know that that's 0. So that tells us at t equals t naught, we have not gone any distance at all. We're still sitting right here. Sitting on the couch, we're not doing much. But if that t is something other than t naught, something for some t greater than t naught, and let's put that restriction on this. S of t is the distance traveled from t naught to some general value of t. So this is a point with coordinates x of t, y of t, z of t. This distance, that's S of t. That's the distance traveled as a function of time. That's how far I have gone since I started, or how far I've gone from t equals t naught to that point. Okay, so that's exactly what we're calculating there. Now let's find the arc length parameter for that function that we just worked with. We had r of t was equal to 6 sine of 2t times I hat plus 6 cosine of 2t times j hat plus 5t times k hat. And now instead of finding the length of the curve from 0 to pi, let's just find the arc length parameter, or the distance traveled so far as a function of time, using this formula. So we're saying for t greater than or equal to 0, so that means 0 is our t naught. S of t is the integral from t naught to t of r prime of tau, integrated with respect to tau. Now we've already calculated r prime. In the previous problem, we showed that r prime of t was 13 from before. This is from the previous problem. Now, if this was 13t, r prime of tau, or if the magnitude of r prime of t was 13t, then this evaluated at tau would be 13 tau. But since it's just a 13, it doesn't matter that that's a tau and that's a t. This is going to be 13 too. Doesn't matter what. Constant's always, it's going to stay constant. T naught was 0. We're told that because we want this for t greater than or equal to 0. So we'll integrate this with respect to tau. Then substitute in tau equals 0 and tau equals t. So you have 13t minus 13 times 0. So we get 13t. So this is the distance traveled along that curve as a function of time. So if you've just got out there, you haven't done anything yet, t equals 0, you haven't traveled any distance at all. S of 0 is 0, no distance traveled. But let's say you've been traveling for 1 second. Well, according to this, you've traveled 13 meters if we're using meters per second and seconds. Meters per second as our units for speed and seconds for our units for time. So this would be 13 meters. And say, okay, well, what happened after 3 seconds? How far have you traveled at that point? Well, that's just going to be 39 meters, and so on. This is nice. It tells me the relationship between the distance traveled and the time. This is a really simple one because the speed happened to be constant. We are going at a constant 13 meters per second. And then I just multiply that by the number of seconds to get the distance traveled. sometimes it's not so, the speed's not so constant. Sometimes you're speeding up and slowing down, and at some points your speed is 0 and all of that. But for this one, our arc length parameter is just 13t. And that tells us how far we've traveled along the curve after a certain amount of time. Now, sometimes we take our arc length parameter and we solve it for t. So I've got this is 13t. So I have distance traveled as a function of time. So s is representing the distance. Now you might say, okay, what if this doesn't represent time? What if we're not talking about motion at all? Fair enough. If this just represents some parameter, as that parameter changes, the length of the curve changes. So this is the length along the curve, which is given by s, as a function of the arc length parameter, or excuse me, as a function of the time parameter, t. And I butchered that when I said that. Let me repeat myself, or let me clarify. If we're not talking about motion, s represents length along the curve as a function of this parameter t. Now the parameter might represent time, and then we're talking about distance traveled along the curve as that object's position changes. If this doesn't represent time at all, but it's just some parameter, this is the length of the curve as a function of that parameter t. Now, I can take this distance traveled as a function of time and I could invert it. Like I could find time as a function of distance traveled. With this one, it's easy enough. I don't really need this of t, so I could say s equals 13t. Well, if that's true, then t equals s divided by 13. Say, well, what on earth does that mean? Well, s is, let's say it's in meters, and we're dividing by a number of meters per second. And when you do that, you end up with s over 13. The meters reduce. You've got 1 over seconds here in the denominator, so it becomes seconds in the numerator. And you get seconds. So if you traveled, let's say, 26 meters at 13 meters per second, you wanted to know how much time, how long you've been out there. Well, you just take the 26 and you divide by 13 and you'd say, I've been traveling for 2 seconds. So this is, if I take this and I invert it, so I'm finding the inverse function of this. Instead of having s as a function of time, I've got time as a function of s. This is the parameter t, which often represents time in terms of the arc length parameter s. And again, s is length along the curve, or if we're thinking of r as a position function, it's the distance traveled in that amount of time. Okay, so now we've got all this. Now let's find position as a function of distance traveled. A lot of students say, why on earth would I want to do that? And we'll talk about why we want to do that in a minute. So let's say this is our position function, same one we've been working on, same one we've been talking about. And we're saying that's our position for time t greater than 0. Maybe instead of talking about position as a function of time, we want to find position, I'm going to call this r star, as a function of distance traveled along that curve. Well, r star of s just comes from taking the original position function and replacing t with whatever it was in terms of s. So I replace t with this function of s. I know that notation looks strange, But all I mean is to take this equation, s equals 13t, and solve for t, and I get t as a function of s. So I'm going to replace all of my t's with s over 13, and I get this. So I have 6 sine of 2 times my t as my x component, and 6 cosine of 2 times my t as the y component, and 5 times my t value as my z component. And I'm going to replace my t with s over 13. So I've got s over 13 here, and s over 13 here, and s over 13 here. And if we simplify that, we get this. 2s over 13, 2s over 13 there, and of course this is going to be 5s over 13. This is position along the curve as a function of distance traveled. This guy was something we were interpreting as position as a function of time. Many students say, why on earth would I ever do this? Well, let's think about it. Is there ever a time when it would be helpful to know what your position is as a function of how far you've traveled? I think so. I mean, think about going to Riverside Drive and jogging. I don't jog much, but if I did jog, so maybe this is Riverside and they've got that beautiful path. And there is Miss Townsend trying to jog along the path. So I'm jogging along in this curve. It might be helpful to know, what is my position? Maybe this is my question. Yeah, if I start at, the parking lot at 41st Street, and I jog for, let's say, 3 miles, wouldn't it be helpful to know where I would end up? This is saying, if I travel this distance along this path, what is my final position going to be? Instead of saying, if I travel along this path for 2 hours, no, I'm not going to jog for 2 hours, that's funny. If I travel along this path for 20 minutes, where am I going to end up? Instead of saying that, I'm going to say, no, I'm not interested in how long I'm out there jogging. I want to see where I would end up after traveling this far. So when I'm interested in questions like this, which deal with position as a function of distance traveled along the curve or length of the curve, so length along the curve, since that initial position, which occurred at time t equals t naught, or the parameter value t naught. If I want this position as a function of length, or position as a function of distance along the curve, then I want to go this way. If I'm interested in motion, I want this. If I want to know my velocity, that's change in position per unit time, right? Velocity is the derivative of this with respect to time. Acceleration is the second derivative of that with respect to time. If I'm not interested in velocity or acceleration, but I'm interested in geometric questions like, where will I be after I travel this distance? I want to use this. So this is for your notes. I ask you a question in the notes about when would I use this versus when would I use this. We want to use r as a function of time when we're concerned about motion. So when our questions are about velocity, acceleration, the time things happen, when we have those types of questions, we want position as a function of time. Now, if I am looking for, or if I'm interested in geometric questions, so questions about length or distance traveled, not just position but distance, and how my curve is changing as my distance changes or as the length changes. This is about the relationship between position and length along the curve. So position, and remember, position is all about location. So it's the relationship between position and location and length or distance traveled along the curve. Then we want to use the arc length parameter. So this is for physics, it's about motion. This is for math, it's about geometry. But sometimes we can have some kind of hybrid of the two, where if I'm talking about motion along some path, I might be interested in my position as a function of the distance traveled along that path, like in my jogging example.